Hello, everybody. This is Roshan. I'm a long-term follower of Numenta. I have been following Numenta since 2015, since the cortical learning algorithm days, which has been pivoted over to hierarchical temporal memory, and I guess now the latest and greatest version is the Thousand Brains project that's been being spearheaded by Jeff and the whole team. Really amazing work that's been going on. Two thumbs up for everybody who's been involved in it. I also have been working on Thousand Brains project for the past 1 year, and I have been following and trying to grasp all the concepts around Thousand Brains project and hierarchical temporal memory for a while. And in this video, I want to share a quick update on where I am with the project and what I've been able to achieve so far. This is Hentul, a quick temporal Thousand Brains project tool that I have created so far, and I wanted to share what it can do so far and how it can be extended. If anybody is willing to work on it, if they have any feedback, they can definitely uh, hook up to me and we can definitely talk more. This is very similar to Monty. It's not definitely inspired by Monty, since I started it working on it almost more than a year back. This is a Windows Form application which I want to show to everybody in the group. And welcome to feedback. This is a Windows Form application. Like I said, it is very similar to Monty in ways that it uses sequence memory, spatial pooler, um, cortical. It uses somewhat a different format of cortical messaging protocol, where intercortical regions can communicate with each other by exchanging messages, and it's all done through sparse distributed representations, which is very important. And there is a couple of new algorithms that I've put in place for object classification and reference frame based object classification, and there's a burst avoidance algorithm that I'm going to talk more towards. And all of this has I have I will link the links to the website or to my website, which has more details about all of these algorithms in the summary above. Um, just want to go over and do a quick overview of what the tool is. This is the Windows Form application that I'm gonna show here. There is a quick status at the top left here. It shows ready, just means that what's the state of the agent and what the agent is doing currently. It's just waiting for an input and it says ready. And once it makes a decision on what the object it is trying to parse, it displays the object label here. This is an unsupervised learning layer, but it can be trained across multiple objects. And in this particular case, I will be training it upon a simple two-dimensional black and white object that's an apple. Um, and here, let me just initiate the system and allow it to start training, and I can talk over what it's doing throughout the process here. So as you can see, it's trying to initiate here, and once it initiates, initializes the whole system, I'm going to hit start training here, and you can see there's going to be two images that are going to pop up. Um, these are the images of what the cursor agent currently sees. The agent only sees a 40 by 20 pixel grid around the cursor, and it's sort of like um, looking through a small straw. If you want to use the Numenta analogy, it cannot look at the entire image all by itself, just like how we do as humans. Even if you talk about the human neuroscience, we do not look at the entire image. By ourselves, depending upon how close or far you are to the image. The human eye has a very small dimensionality. It doesn't look at the entire image, but the vision feels like you're looking at the whole thing all at once because of how good our visual system is in processing all the information, making trillions of decisions all at the same time parallelly to create this conscious experience. But my tool is not at that point right now. So as you can see, it filters out the image on the left you see is the actual image, and the image to the right that you see is the grayscaled out image, which removes all the color information. It removes all the Since it's a two-dimensional image, it removes out any orientation or um, any orientation information that the agent might see. So it goes through the entire parse, tries to parse through the entire image, and that's all that it sees. And through this information, it is going to make a decision on what kind of object it is currently pursuing. Right now, it is just in learning mode. It's not in prediction mode, so it is just trying to learn as much as it can about the object. Um, um, Once through this process, I want to talk a little bit more about what's actually happening under the hood. There is quite a lot of logic that's going on under the hood. There is multiple neuronal layers, and this is I have used layer two, three, and layer four of the cortical column since it's not processing any orientation or color information. This is just one layer 3A, layer 3B, and layer 4. That's three different layers and a couple of other modules for orchestration and hippocampal and grid cells in the entorhinal cortex module that I use to store locations and sensations of how the agent is actually viewing the world. I'm digging a little bit deeper into some of these layers. The input primarily comes in through layer four. I will write detailed synopsis on how the agent actually works under the hood. But I'm going to go over through quick tidbits of how the agent is actually processing all this information. So the image pixel data that you see primarily goes through some encoders, which sparsifies the inputs and projects it down to layer four. Layer 4 being the primary input layer. These are all feed-forward cortical mini-columns, which project all the information directly up to layer 3A and layer 3B. And layer 3 and 3B are second-order memory, which just means that it has broader lateral connections among the layer. And layer 4 being an input layer, it is a first-order memory, which means that it doesn't have lateral connections, long range connections among it. It does have proximal connections, which are very local to neuron scope and to just nearby neurons. It doesn't span across multiple different um, area scopes within the region. So there's three different layers, and the feed forward input goes from layer to layer, starting from layer 4, and the layer 4 inputs are projected over to layer 3A, and layer 3A is a pooling layer, which is a temporal pooling layer, which comes into effect once the decision has been made on what the object is. If the object decision has been made and the agent knows what the object is, then layer 3 is the temporal pooling layer, which avoids any bursting in layer 4 cells once the agent starts moving across the object, kind of feel and sense more information on the objects. And uh, the information also goes to something called as layer 3B, which is a classifier layer, which works with the hippocampal entorhinal cortex module, trying to determine what the object actually is. And in this particular example, um, layer 3B, while it is in learning mode, it tries to absorb all the information it can as possible, and it connects to a hippocampal entorhinal complex module, which connects with layer 3B, and it stores all the locations, different locations that it is sensing on the object and stores it locally. Um, I will add more details on specific details on how the algorithm actually works. I'm going to speed this up so we can see what the program actually does here. Now that I have sped up the process, the agent has finished processing the entire image. As you can see, it says finished processing the image, but it has still not recognized the object label. Here you see a new button that has come up that's saying test classification algorithm. This is the reference frame object classification algorithm that I was referring to earlier. What it actually does is once I click on it, it's going to start parsing through the entire image, and once it senses any important sensations, then it's going to start making predictions, as opposed to how it has seen these similar sensations before throughout its lifetime. And using the complex module and grid cell module on the specific location that it is on the object, and the historical experience it has had, it's going to start making predictions, and it's going to start validating those predictions by performing motor actions on the image, parsing through the object. And once it has sufficient number of predictions, then it's going to classify the object and print the object label over here. So let's just see how it works. So as you can see, it's processing through the image. This takes a little bit of time, since for every layer, I think there's 4,000 to 5,000, 5,000 actual neurons per layer, and then there is 3 to 4 layers, so that's 15,000 neurons. And this is my personal laptop with a 32 GB RAM and i7 Ultra chip. So still takes a little bit of time. It's not too bad. But if I were to simulate something similar to 45,000 or 100,000 neurons, then my laptop would definitely be starting to sweat. As you can see, it takes a little bit of time trying to process. The code is not super optimized. It's taking in the sensations and trying to figure out what predictions to make, and it works with all the other neurons and exchanging messages. Now we can see it has moved a little bit, and taking in sensations, it's making predictions, and if the predictions fail, it moves over to and it starts from scratch, trying to figure out what the object is. In this particular example, there is a lot of nuances and design decisions to create this reference frame classification algorithm that I have done. It took a lot of time and careful decision making and strategic decision making to make the code as extensible as possible, because in the future I'm planning on implementing this for color as well, and then even orientation of the object, making it support for three-dimensional objects, so that it also holds object classification, object orientation information as well. And then there is the second algorithm that I'm going to be showing out, is the burst prevention algorithm. That is, once the decision has been made and the agent knows what this object is in its universe, and this code is that I've created, it's all in .NET Framework and it's C#. You don't need any additional packages. All you need is just a Windows laptop. You can download the code, download Visual Studio, run it, and hit start, as I did, and it should work just fine. And as you can see, it says here object is recognized and the object is Apple. And you see there's one more button that has popped up. That's the test burst prevention. That's the algorithm that I was talking about. So now that the decision has made, the agent knows that it's an apple and what locations it's exactly on and what kind of sensations it's supposed to feel. Now, what test burst prevention does is it's gonna indicate to the agent that, hey, you can roam through the object however you want, and if the pixels, if you're feeling any sensation that it shouldn't be there, just start firing, and that's gonna throw a bunch of exceptions and the code is gonna crash. But hopefully that won't happen, and if it doesn't happen, it'll just roll through every single iteration. So let's test burst prevention. As you can see, it's pretty quick. I'm not sure even if it got recorded. It was that fast. I'm going to try and do it again and see if people can see it. Once I click test preparation, it goes through the leaf area of the apple, goes through every iteration, and it just starts roaming through a bunch of these locations and sensing and matching with the hypothesis that it has. So this is all happening with the in the layer 3A predictions that I was talking about. Layer 3A being the temporal pooling layer, it has control over layer 4, which is the input layer. And once the decision has been made, temporal pooling layer, the layer 3A controls all the burstings. And if there's any single burst on layer 4, that just means that the prediction miss. There is no prediction hit, and it has to go back, and it completely throws off the system that, hey, I had already made the decision. Why is the neuron still bursting in input layers? So these are the two algorithms that I wanted to talk. There's a significant amount of work and thought that I have put in through these both of these algorithms that I don't think Monty has implemented the burst prevention. I'm not sure how they are doing confirmation. I would love to learn and see if any of you have any feedback, and definitely would appreciate any contributions or any feedback you guys have. You can put it down in the comments. Yeah, thank you.